Good morning everybody and welcome to another video. To begin this playlist, we're going to be looking at some basic definitions that are needed for aerodynamics. Specifically in this video, we're going to be looking at pressure. So pressure is simply another unit of measurement that we use in physics. It's similar to something like force or velocity, where force might equal mass and acceleration and velocity might equal distance over time. Pressure is equal to force over area. So we use pressure to measure the amount of force on a surface per area. And just like we might have kilometers per hour, with pressure we have newtons per meter square. 1 newton of force per meter squared can also be expressed as 1 pascal of pressure. So 1 pascal of pressure is the same as applying 1 newton of force on an area that is 1 meter squared wide. So there's 3 different ways that we can view pressure that I'd like to share with you today. Viewing pressure as stress, viewing pressure as the sum of particle forces, and viewing pressure as a relationship between force and area. So in physics, you might learn that when you apply forces on an object, that object will either move or remain still. So I'm sure you've already done lots of exercises where you grab the sum of forces and you find out which direction it's either accelerating in or not accelerating in. But pressure, which is a type of stress, will help determine whether an object is going to break or bend. For example, in physics, you might have a look at a diagram like this, where you've got a 70 kilo weight that's under the influence of gravity, resting on top of another object that's on the ground. And in this scenario, if you disregarded the shape of the objects and just assumed that they're directly above or underneath each other, then you would assume that this object would hold up the other object with an equal amount of force, just like so. If you can imagine that this has a human foot, even though it's a bad drawing, and that person weighs, 75 kilos, like the example before, you got 75 times g amount of force on the ground, and the ground happily supplies 75 g newtons of force up on the foot, and both objects are at rest. And the foot does not bend or break because all that force is being put on a wide area on the ground. If, however, the foot was not supported by the ground, but instead all that weight was supported by something very small, like a piece of Lego, all of a sudden that foot is not happy, and it might even bend or break. Because of this very small area and the same amount of force, you have a lot higher pressure on the foot. It's the same scenario, 2 objects at rest, but different amount of stresses. Now, I hope that analogy helps you clearly understand pressure as force on the surface of an object. But this is aerodynamics, and we're studying gases. And gases don't have surfaces like this. Even when there are no objects in the air that have surfaces that forces can act on, we still describe pockets of air as having pressure. You might say, oh, the atmosphere has this much pressure, or the air inside my tire has this much pressure. So how can air have pressure if it's not a surface being influenced by a force? This all comes down to our basic chemical understanding of what a gas is. So I'm sure you've already heard in chemistry that a solid is just a bunch of atoms closely grouped together. A liquid, they're moving around a little bit, and in a gas, like air, they're moving around a lot like this. So imagine these atoms just floating around in air like a gas. If I was to put an object inside of this gas, like so, you can see that some, not all, but some of the particles are directly hitting this solid object. And when these atoms that are moving around hits the surface of the object, it creates a force over the surface. Now this is only a very crude diagram with only about 8 or so atoms, but obviously in real life, even the smallest amount of air will have thousands or millions of atoms. And so you can guarantee that in each area of air around the object, you always have some atoms hitting it head on and creating force. And so, assuming that pressure is the same across the object, the force across the surface of the object should also be the same, and the amount of force on the object should be proportional to the area that is experiencing pressure. So if we wanted more pressure in the same volume of air, how might we go about it? Well, ignoring the physics side of things, you've probably already heard people talking about instances of high pressure and low pressure. If you have an air compressor or a balloon, then you've got lots and lots of air in a very, very small space, and that creates high pressure. But if you have a vacuum chamber, or perhaps as you leave Earth's atmosphere, there will be a lot less air in the same amount of space, and that will create low pressure. Looking at this example here, it's easy to see why more air in the same amount of area will create a lot more pressure. If you double the number of atoms that are floating around, you're going to double the number of atoms that are hitting this object. So if you have twice as much air in the same amount of space, you're going to have twice as much pressure. The amount of air that we can pack into a certain amount of space is known as density, where density is equal to the mass of the air per unit of volume, or in SI units, kilograms per meter cubed. But we have to make sure that we remember that pressure is not just density. Pressure doesn't just rely on how many atoms there are moving around in a space, but also how quickly they're moving and how much energy they have. And we have a word in chemistry for intermolecular kinetic energy, and that word is heat. Heat is just how much energy there is between molecules moving around each other. And so the more heat there is, the more these molecules are going to move faster and faster, the harder they're going to hit the objects that are within them, and the more pressure there'll be. So pressure is proportional to heat and density. It is proportional to the amount of movements between molecules and the amount of molecules there are in a certain area. And this here is pretty close to what's known as the ideal gas law. The ideal gas law says that pressure is equal to density times temperature times a specific gas constant. But assuming you're using the same gas, this constant won't change, but the density and the temperature might change. So the last thing that I want to talk about is how pressure doesn't just describe how things will bend or break, but also describes the relationship between the area of an object's surface and the forces acting on it. Let's say we have a sailboat and we have wind that is hitting the sails on the sailboat, and we want to find the force of that wind on the sailboat. This is a little bit of an oversimplification, but we can find some numbers to plug into this equation to figure that force out. Let's say, for example, that the drag coefficient is going to be 1.28 because we're dealing with a flat sail. The density of the air is going to be 1.293, or we'll just round that up to 1.3 kg per meter cubed. And we'll assume on this day that the wind has a velocity of 15 kilometers per hour, or 4.2 meters per second. We find that we have a drag pressure of 14.67648 pascals, which for argument's sake we can round up to just 14.7. So what this means is that if we know the pressure that the wind applies to the sail, we can work out the force that this wind is exerting on the boat relative to the size of the sail. For example, if this sail is 1 meter squared wide, so we have 1 meter squared of area, then we can take our formula for pressure, which is pressure is equal to force over area, and we can multiply both sides by the area to rearrange it to make force the subject. So force is simply going to equal pressure times area. So in this instance here, where we have an area of 1 meter squared, and we know that the pressure from the wind is 14.7 pascals, we can say force is equal to 14.7 times 1 meter squared which is equal to 14.7 newtons, which is equal to 14.7 newtons of force acting on the boat. And say we have a bigger boat with a sail that is 3 meters squared wide, then we can use the same formula here. So we can say the force acting on the boat is equal to the pressure from the wind times the area of the sail, which means it's equal to 14.7 times 3, which means the force acting on this boat is going to be equal to 44.1 newtons. And you notice here, even though we're talking about pressure, this has nothing to do with the stresses acting on the boat. This sail here is not experiencing any more stress than this sail here, but it's the forces that are different. It experiences a larger force because of a larger area. Pressure is just the relationship of force per area. And this explains so much in aerodynamics, how the size and the shape of an object can change the forces acting on it. It's why parachutes are so big and wide. It's why airplane wings are so big and wide. It's why if you take 2 sheets of A4 paper and scrunch one up and keep one flat, that they fall at different rates. They both weigh the same, so they both have the same downwards force, but one of them only has a very low upwards force, and one of them has a much higher upwards force. Because of its large area, it means that the pressure from the air has a greater effect on it. So I hope that gives you a good understanding of what pressure is.